Hi everyone, this lecture will be about reproducible research, and I want to talk about some concepts and ideas that are related to reproducible research, and just in case you haven't heard about it or don't know what it is. So the basic idea is that in science, replication is the most important element of kind of verifying and validating findings that scientists discover. So if you claim that X causes Y, or that vitamin C improves disease, or that this causes a problem, what happens is that other scientists that are independent of the original will try to investigate that same question and see if they come up with the same result. And if lots of different people come up with the same result and replicate the original finding, then we can tend to think that, well, then the original was probably true and that this is a real relationship or real finding. So the ultimate standard in strengthening scientific evidence is replication, and the goal is to have independent people do independent things with different data, different methods, in different laboratories, and see if you get the same result. Because if a finding is robust to all these different things, then it's more likely to be true, and the evidence is stronger in its favor. Replication is particularly important in studies that have big policy impacts or kind of influence regulatory types of decisions. So, what's wrong with replication? So there's really nothing wrong with it. This is what science has been doing for a long time, through hundreds of years, and there's nothing wrong with it today. But the problem is that it's becoming more and more challenging to do replication or to replicate other studies, and part of the reason is because studies are getting bigger and bigger. In order to do big studies, you need a lot of money. And so there's a lot of money involved, and if you want to do 10 versions of the same study, you need 10 times as much money, and there's not as much money around as there used to be. Sometimes it's difficult to replicate a study because if the original study took 20 years to do, it's difficult to wait around another 20 years for replication. So that can be a challenge. Some studies are just plain unique. So if you're looking at a unique situation in time or a unique population, you can't readily replicate that situation. So there are a lot of good reasons why you can't replicate a study. And so the idea is that, well, if you can't replicate it, is the alternative just to do nothing, just let that study stand by itself. And so the idea behind reproducible research is to create a kind of minimum standard or a middle ground where we won't be replicating the study, but maybe we can do something in between. So the basic problem is, you have the gold standard, which is replication, and then you have the worst standard, which is nothing. And so what can we do that's in between the gold standard and nothing? And that's what we're thinking is reproducibility. So that's how we can kind of bridge the gap between replication and nothing. So why do we need this kind of middle ground, which I haven't clearly defined yet, but the basic idea is that you make the data available for the original study, and you make the computational methods available so that other people can look at your data, can run the kind of analysis that you've run, and to kind of come to the same findings that you've found. And so a lot of this, what reproducible research is about, is a validation of the data analysis. Because you're not collecting independent data using independent methods, it's a little bit more difficult to validate the question itself that you're asking. But if you can take someone's data and reproduce their findings, then you can in some sense validate the data analysis. And so this involves having the data and the code, because more likely than not, the analysis will have been done on a computer using some sort of programming language like R. And so if you can take their code and their data and reproduce the findings that they come up with, then you can at least have confidence that the analysis was done appropriately, and that the correct methods were used. So what is driving this need for kind of a middle ground, this reproducibility middle ground between replication and doing nothing? Well, there's a lot of new technologies on the scene in many different fields, including biology and chemistry and environmental science, all kinds of areas. These technologies allow us to collect data at a much higher throughput. And so we get these very complex and very high dimensional data sets almost instantaneously compared to even just 10 years ago. And so the technology has allowed us to create huge data sets at essentially the touch of a button. Furthermore, we have computing power that allows us to take kind of existing databases and merge them into just even bigger and bigger databases. So we can take data that were previously maybe inaccessible and create new data sets out of them. So these new data sets are huge now. And in addition to allowing us to create new data sets, Computing power allows us to do more sophisticated analyses. So the analyses themselves, the models that we fit, and the algorithms that we run are much, much more complicated than they used to be. And so having a basic understanding of these algorithms is difficult, even for a sophisticated person. So understanding what someone did in an analysis of data will require looking at code, looking at the computer programs that people used. And so the bottom line with all these different trends is that for every field X, there is now computational X. There's computational biology, there's computational astronomy, computational whatever it is you want, there is a computational version of it. So one example from research that I've conducted is in the area of air pollution and health. Now, air pollution and health is a big field, and it involves is a confluence of features that make reproducibility very important in this area. The first is that we're estimating very small but very important public health effects in the presence of much stronger signals. So you can think about air pollution as something that's perhaps harmful, but even if it were harmful, there are many other things that are going to be more harmful that you have to worry about. And so pollution is going to be not at the very top of the list that's going to harm you. The results of a lot of air pollution research inform kind of substantial policy decisions. Regulations will be based on scientific research in this area, and so these regulations can affect a lot of stakeholders and furthermore can cost billions of dollars to implement. Finally, we use a lot of complex statistical methods to do a lot of these studies, and these statistical methods are subjected to intense scrutiny. So the combinations of an inherently small signal, large impacts, and complex statistical methods almost require that the research that we do be reproducible. And so one of the things that we've done here at Johns Hopkins is to create what's called the Internet-Based Health and Air Pollution Surveillance System, where we make a lot of our data available, we make a lot of our statistical methods in the form of R code available, so that they can be examined and the data and many of the results that we produce can be reproduced by others.